morning. Oh, there's another person. I just got behind trying to, actually enjoy life for a change. Got Alexis. Alrighty. For the opener today, if you have a beaker or an Erlenmeyer, like the glass, the Pyrex stuff that we use, and you're mixing different chemicals together. Now, how would you know by touch? I mean, you're not sticking your finger in the chemical. Okay, so the outside of the beaker. How would you know by touch if it was endothermic or exothermic? That's exactly right. If you react, so sorry, all my allergies are horrendous. If it is endothermic, it has to bring heat into itself to be able to go over that hump. And it's going to feel cold to the touch. It's what happens when you crack a glow stick, a light stick, and you shake it. They're cold to the touch. If you don't believe me, just pay attention next time you do it. I promise you they're endothermic. If it's exothermic, it has to give off heat in order to create the products. And that's going to feel warm to the touch. Now, please don't stick your hand in fire, okay? But when things burn, they are exothermic. They're giving off heat. I shouldn't have to tell you not to stick your hand in fire, but
I've got myself on fire.
Oh.
I was gonna pull some patties off the grill when I didn't have any tongs and I had to wash them with
Friday? Really?
Sure the heck did.
Oh, goodness.
I took a wine from the ash bottle.
No. No.
Like 6 and I grabbed it.
All right. So, some of this stuff, y'all, some of this stuff is just yanked off of, yanked out of, because there's only 2 of them that are on this test. There's only 2 topics on the test. So I think there's 25 questions on the test. And I went ahead and turned around and created the test myself because some of the other teachers are skipping this and they're going directly into nuclear. We're not going to do that. We're going to go ahead and test over this little unit. And then we're going to start nuclear chemistry on Wednesday. And there isn't much left. Like I said, we've got, there's not much left. So nuclear will take us, I'm still building your module for this week. Through this week, as far as work days, I haven't figured out if we're going to need any of those yet. I'm sort of going to let the way that y'all understand or don't understand the nuclear chemistry, if we're going to need to stop and go back and push stuff forward. But yeah, after next week, that's it. It's not that we have a semester test, but 6 weeks exam week. So, all right. So what changes how quickly a reaction occurs? The biggest, now it does depend if you're dealing with solids and liquids, because that does make a difference, but in general, and it's sort of a blanket statement, temperature. If the substance is warmer and you apply heat, in general, it's going to make the reaction happen faster. There are some exceptions, but I'm not going to try to trick you on the test. Because like I said, I got to make a test this time. I didn't even get it from this count. So if you have a higher temperature, your particles, because temperature is kinetic energy, okay? And the faster they're moving and they're bouncing off of each other, the more interactions are going to happen because they're moving faster. And if they're moving faster, eventually they're going to bind the right way and they're going to make a product. So as a whole, if you increase the temperature, you're going to speed up the reaction. Concentration. If you have more stuff that you're mixing together, there's less room for that stuff to move around. So they're going to slam into each other more often, and they're going to have a higher chance to actually interact with each other to make said product. And I know I had put glucose up here. I know I did. That not that you need to, but I'm about to put on the board, those of you that don't know, this has nothing to do with the test. It's just to show an example. So water, H2O, which looks like this. Carbon dioxide, which looks like this. though. Alright, so, no, not COVID, pollen. Like I said, I'm hoping that the rain that we're about to have the next few days fixes this, because I'm getting really sick and tired of it. So with concentration, the more stuff that you have, like I said, the more often they're going to slam into each other, the higher chance that your molecules that you are reacting, in this case carbon dioxide and water, are going to line up just right, and they're going to make a product. How big your reactants are. Okay, so the best example I have is a sugar cube versus like granulated sugar, loose sugar. They're both going to dissolve, okay, but your cube, even though it's the same amount as its equivalent in fine sugar, it has to do with how much surface area is present. So if you have a solid and you crush it up and you try to mix the things together in whatever, beaker, flask, whatever, then you're going to have more interactions on their surface themselves. And then the one thing that we really haven't gotten into is something called a catalyst. It's not used in the reaction. It's not a product. It's still there. It's there at the beginning and it's there at the end. But what it does is it helps to accelerate your reaction. That pump, the graphs that we're going to do, and we're going to go over it once again, that pump, it makes it smaller. It's still there. It's just not as steep of a hill to get over, just like a roller coaster kind of analogy. So these are the four things that will affect how quickly your reaction happens. Increasing the temperature, increasing the concentration, decreasing the particle size, or using a catalyst will all make a reaction go faster. So now if I do this, so see if I remember how to draw this from scratch. CH2 OH which is up and which is down, and this has particles. I don't know which one's up and which one's down. I'm gonna have to cheat using phone. It's been a very, very, very long time since I've done biochem. Don't know. Don't know. Okay, so down. Down is first. But so like inside a plant, when they breathe in carbon dioxide and they use water from the soil within their tissues, eventually they make the product and they give off oxygen gas too. But so these things, and I know, I mean, you're not going to heat up the plant, okay, but the faster that things happen, and in this case, solar energy, they're going to switch from your starting substances to, and this happens to be one of the final substances. The other one is this. Six, yeah. But that actually was what happening. If you could zoom in and take a look at the reactants and the products, that's what you would see. Now we did this the other day. Who's this? Who's this? Where's Declan? Ah, it's the right one. There it is. You do need to know your temperature scales. You do need to know how to convert between Celsius and Kelvin. There are questions that are that simple. But we're used to we're used to the Fahrenheit scale, which is based off of the boiling and the melting point of alcohol, of ethyl alcohol. The boiling point of water on the Fahrenheit scale is 212, Celsius is 100, And in the Kelvin scale, when you add, bless you, when you add 273, it's 373. These are all the same thing. The freezing point of water in the Fahrenheit scale is 32. Anything below that's going to turn water into ice. In Celsius, that's 0. And in Kelvin, when you add 273, because that's the magic number to go back and forth, it's 273. Once again, these all mean the same thing. They're just a different temperature scale. Rated on the absolute scale, okay, absolute 0 is the point at which electrons stop moving around the nucleus. Okay, in Fahrenheit, that translates to negative 459. Rated. In Celsius, it's negative 273. And in Kelvin, it is 0. And this is why we did our gas law math in Kelvin, because it's not negative. Negatives mess up gas law math. Now, in calorimetry math, which I believe I put into the grade book for progress reports, it might be the only thing you still have to turn in. It really doesn't matter if you're Celsius or Kelvin because the jump is the same. And so when you subtract the final minus the initial temperature for the delta T, it's still the same value. Doesn't matter if it's Celsius or Kelvin. However, in the gas laws, when we did that, it had to be in Kelvin. It couldn't be in Celsius. I'm not expecting you guys to miss the questions that are temperature conversion like this is. If you are wanting to change it into Kelvin, I didn't put the degree symbol next to the Celsius like I should have, but I'm not worried about it. If you're in Celsius, you add 273 to get to Kelvin. Okay, if you're in Celsius, or if you want to get to Celsius from Kelvin, if you're in Kelvin, then you would subtract 273 to get back to Celsius. Kelvin does not get the little degree symbol, Celsius does. This was the other equation that we took a look at, where your heat, which could be calories or joules, I don't know. It depends on what your specific heat is being done in. Or your specific heat is going to depend on what your heat is being done in. But if they're either going to match calories or they're going to match joules, but your mass is going to be in grams. Probably could have made this a little bit bigger. Your specific heat, so either the calories has to match and it's divided by grams degrees Celsius, or your joules is going to match per grams degrees Celsius. Now, sometimes you'll see this as a Kelvin. It does not matter. It just doesn't matter. Your change in temperature could be Kelvin or Celsius. When you take the difference is going to be the same, whether it be Celsius or Kelvin. It just doesn't matter. I was always taught to change to Kelvin no matter what. That's just what I was taught to do. I did not put this up for myself. Oh, I needed to rain yesterday. The horse apples. Yes, it's horrible. Like I said, I'm hoping that the rain's going to wash it out. But as long as the male tree for the horse apple keeps pollinating, it's going to this. Apparently I'm allergic to horse apple pollen. Yeah, horse apples are like softball size green brain looking things. Apparently.
Oh, no. Like 72 times bigger than
Apparently this is what it does to me. I've never even knew I was allergic to it until, what was it, the middle of last week? I'm gonna find that tree. I'm gonna cut it down. All right. We're gonna see if I can draw on the smart board again. Because it worked. It worked last week. Don't jinx it. Don't jinx it. I'm about to find out.
No.
Okay, so you have to be able to identify all different kinds of things on these. The one on the left is endothermic. I know this is endothermic, besides it says it's endothermic from sight because the uphill slope is bigger. Okay, and I know that the one on the right is endothermic because the downhill slope is bigger. And they're still going to have potential energy for your reactants, your products, your activated complex. We're still going to have an activation energy, and we're going to have an enthalpy or a change in heat value. So let's see. So it works. It's amazing what happens when you update your software. This would be my potential energy for my reactants. Okay, it's from the flat line on the left down to 0. So this is 0. Let's call this one 20. Yeah. So let's call it 20, 40, 60. Let's 40, 60, 80. Okay, let's call this 100. Call this 80. It doesn't really matter. I mean, you'll have data on the left-hand side to be able to subtract. So in this case, my potential energy for my reactants, it's already at 20 kilojoules. And my potential energy for my products will be the flat line on the right-hand side. The hump is the arrow of a chemical equation. So from the products down to 0, in this case would be 80 down. This would be my potential energy for my products. It's just, they're not hard. It's just a matter of figuring out what are you subtracting. Okay, and then my potential energy for my activated complex, this is what makes the reaction actually happen. You're not going to make products until you get over this hump. And like I use the roller coaster analogy. You could be going up the track with the roller coaster, and if it stops here, hopefully the brakes work on it. Otherwise, you're going to go backwards. So this would be my potential energy of my activated complex, which in this case would be 100 kilojoules. Your activation energy isn't from 0, it's from where you started at the reactants up to the top of the hump. So my activation energy, which is already sort of drawn here, EA, in this case would be 100 minus 20, which is 80 kilojoules. And then what am I forgetting? My enthalpy. My enthalpy is from the reactants to the products. This is my heat, which would be 80 minus 20, which is 60. Now, you do need to know if it's positive or negative. If you put heat in, it's positive. It's on the kilojoules are on the left-hand side of the arrow. It is positive. And it's not going to work unless you put energy into the system. And it's going to be different on the other side. Let's do exothermic. Once again, I know this is exothermic because my downward slope is much larger than my upward, but you still have a potential energy for your products. I'm going to use the same numbers. It was 0, 20, 100, so I'll make this 120. Okay, this would be my potential energy for my reactants. That's supposed to be an R. And then my products, this would be, let's call this 40. It's not the straightest of dotted lines, but I'm just glad I can write on it. So this would be my potential energy for my products. In this case would be 40 kilojoules. I'm going to have my potential energy for my activation complex, A, which would be 120. In an endothermic reaction, the activation energy is always larger in relationship to an exothermic. It's going to be smaller. This would be my EA, which would be 20 kilojoules. And then my enthalpy, or my heat of reaction, would be 100 minus 40, which would be 60. Now, this is negative. It's giving it away. The one on the left was having to bring it in, which is why it was positive. If it's written out, like if I did this, which So we're gonna do carbon dioxide, plus water, makes glucose, and oxygen. Okay, so if your kilojoules, whatever it is on this side, it's positive. If it's on this side, it's negative. Giving away, having to bring in. Because you have to be able to do both on the test. You have to be able to yank stuff off of a graph like this. And you also, and I'm pretty sure I put one on the review. You also have to be able to, I did. We're about to do that here in just a second. All right, let me erase the ink on the slide. No. Yeah, we already know the eraser doesn't work right. It draws. Just glad I can write on it. I remember how mad I got at this board at the beginning of the year. All right, so we've got hydrogen gas reacting with liquid bromine to make hydrobromic acid. And then we see energy. Now, if it's on the right-hand side, I just told you, is that going to be positive or negative if it's on the product side? If it's produced, it's given off. It's removed from the equation. So on the right-hand side, that is a negative heat or enthalpy, delta H value. This is what I mean by left to the right-hand side of the arrow. Now I know I'm going to have to come back because the way that this is animated to figure out if it's endothermic or exothermic, because it's just the way that it's animated. However, on this one, we've got carbon dioxide gas reacting with water. We have a value of energy. I do not know what C2H4 is off the top of my head. And oxygen gas. It's not propane, it's not methane. Might be butane. I'm not sure. I'd have to look it up. If it's on the left-hand side, it needed to bring in heat. So would this be positive or negative? Positive. If it's on the right-hand side, it is given off, it is released, it is negative, it is exothermic. If it's on the left-hand side, it has to be brought in, used, or it ain't gonna work, which is gonna be positive, and that's gonna be endothermic. You have to be able to do both of them. We'll do a couple of temperature conversions, although I'm like confident that you guys can go between Celsius and Kelvin at this point. Let me check. I'm slate. I know my head is in your way. Give me just a second. Oh. Okay. There's really not too much to this test. I said there's only 2 topics. I think there's like 3 with nuclear chemistry. All right, we're going to convert. How do you get from Kelvin to Celsius? Do you add or subtract? You subtract. The influence number is 273. When I do 303 minus 273, I get a whole whopping 30 degrees Celsius, which is a bit warmer than what it is in this room. I think 25-ish is room temperature. And then if you're in Celsius, how do you get to Kelvin? You add negative 75 plus 273 or 273 minus 75, same dang thing. That's way higher than it should be. 198. I mean, like it's not down where it should be in the spot off a tip. This is what we did on Friday. And this formula Q equals MC, sometimes it's CP, but C delta T. And I have 75 grams is my mass. Going from 24 to 575, it's final minus initial. And then I would have to look up the specific heat of glass. Now, I'm not gonna make you use that chart. I'm gonna give you the specific heat that's necessary for whatever said substance is. But it needs to be, and I didn't put the triangle on here because I didn't feel like fighting Google Slides to make a simple thing. 525 minus 24 is 551 Celsius. Does not matter, I'm in Celsius. If I change this to Kelvin, it would still be 551, the difference between them. My mass is 75 grams. I would look up the specific heat of glass, which I did for you. Now, this wants it in joules. Oh my gosh. This wants it in joules, so I have to use the joule per gram degree Celsius, not the calorie per gram degree Celsius. They just have to match. I'm gonna give it to you. Don't try to trick you like that. Not me. And then my formula, my heat, which is what I'm solving for, is my mass, which is 75, times my specific heat, which is 0.5, times my difference in temperature, which is 551. I just left the triangle off because, like I said, I didn't want to fight Google Slides. It's so much easier to do this in PowerPoint. PowerPoint just doesn't translate that well to Canvas. So this is a straight multiplication question. When you throw everything in, now I didn't round it, so it would be 3 sig figs. So 20,700 joules would be the correctly rounded answer by sig figs. I just didn't. That's what the calculator told me. Like I said, I literally was putting this together this morning and was finishing at like 8:15 because I got behind. Not that I don't like my chemistry class. This is very, very, very busy weekend. But this is pretty much all that's, oh, it says convert this to calories. 1 calorie is 4.18 joules. I didn't do that on here. All right, I'll do it on the board. All right, so if I'm going to use my actual value, because you don't round when you convert, 20,662.5. This is in joules. The way that we convert, it's 1 calorie is 4.18 joules. So 1 calorie is 4.18 joules. Obviously, I don't have this calculator. Calculator up. 20,662.5 divided by 4.18. And according to my calculator, the answer is 4,943.2 if I'm around one number after the decimal calories, which I want 3 sig figs. So 4,940 calories would be the correctly answered thing by significant digits. I didn't realize I left that off on the thing when I was told that. Did not leave it off on purpose. Now we have 15 minutes left in class. Some of you may still have the calorimetry thing to turn in. I did get one from George, Bailey, Lucas, Sahara, Caitlin, Jared, Mia, Reagan, Jimmy, and Kyle. I did get yours, and they were put into the grade book by the time they pulled stuff this morning. I did drop a daily grade. I've had people already asking about turning in notebooks. We're not ready. Nuclear is. Here we go. No, that's just intro radioactive. Well, nuclear is long. Oh no. The office all fun with it. It's rough. Nuclear is rough. Like I said, if we need to move things around, here, let me look at the calendar for Kim. It's a very, very, very fluid document. Let me see here. according to what we put together the other week, we've got notes 52, 53, and 54. I don't know. I don't know how we're gonna do this. We'll have another test on Unit 12, which is nuclear, probably next Friday. I haven't gotten that far. Like I said, I literally was building this morning as I got here this morning. I'm working on it. Let's see. Let me stop this.